Okay, we're starting. So we are currently in 4.3. We're talking about linear independence. We saw that one of its main uses is to just get rid of redundancies, and there are going to be some other uses. Just to remind you, definition. Well, it's a theorem really. So the definition of a bunch of vectors are linearly independent if you can express one vector in that group as a linear combination of the others. There's a theorem that some people take as a definition because they're very intimately linked. Is we say that V1, V2, Vn in some vector space V are linearly independent. And we can define this in terms of an equation. If C1V1 plus C2V2 plus Cn Vn equals 0, what is it about this equation that we make it linearly independent? Has only the trivial solution, right? So it has one solution and exactly one solution, and that's the trivial solution for the coefficients C1, Cn, i.e. C1 equals C2 equals equals Cn equals the scalar value 0 from your field is the only solution. If there are more solutions, it's not linearly independent. As long as one of these guys is non-zero, you can just bring everyone else to the other side, divide by that guy, and write one of the vectors as a linear combination of the other ones. Okay, so that's linearly independent. So one of the main reasons is this ensures no redundancies. Right? Among some other things. There are a lot of times where proofs can work out when we know about linear independence being involved. Okay? So I gave you the definition. Did I give you any examples? So I just stopped at the definition. Okay, so let me give you some examples now. Example. In Rn, we spoke about the standard basis vectors is a linearly independent set. Right? The set of basis vectors. So specifically, and I'm saying this just for familiarity and no other reason, in R2, the vectors I and j are linearly independent. In R3, the vectors I, j, k are linearly independent. You set them up. So, example, in R2, if you set up C1 times I plus C2 times j, that's just C1 times vector 1 comma 0 plus C2 times vector 0 comma 1. This is just equal to C1 comma 0 plus C2 0 comma C2, which is equal to C1 comma C2. So if I set this equal to the 0 vector in R2, which happens to be the vector 0 comma 0, then I'm forced to choose C1 and C2 equals 0. And a similar thing happens for larger dimensions, right? You literally have just the coefficients are in all the components going down, and each individual component must be equal to the 0 vector in Rn, which is 0, according to the standard set of operations. Another example, in Pn, right? So remember why this is familiar. I use the same examples for spanning sets, but they also happen to be linearly independent. And it's kind of why they're the standard ones. So the set 1 comma x, x squared, all the way up to x to the n is linearly independent. Right? And you can kind of justify that as well. I can take, say, c0 times the vector 1, c1 times the vector x, c2 times the vector x squared, times cn times the vector xn, and set that equal to the 0 vector in the polynomials, but that's just the vector 0 plus 0x plus 0xn, x to the nth power. By equating coefficients, you can get right? The constant term over here must be the constant term over there. The number of x's over here must be the number of x's over there, etc., etc. You just get c1, c0 equals c1 equals da da da. All of them ultimately are just 0. So those are some nice answers in English standard. Let's do sort of a non-standard. Let's do a couple non-standard examples. And then I'll move on to some more ideas. So determine if the following are linearly independent in R3. With the standard operations. So let's say we're looking at R3 with the usual way we do vector addition and scalar multiplication. Are the following sets linearly independent? So S1, this is the set of 3 vectors, 1, 2, 1, 0, 1, 1, minus 1, 0, and B is 2, 1 minus 1 minus 2. So how would you go about doing that? What would you do here? So we're doing A. How would you check linear independence? Huh?
Set a matrix.
What do you mean set them equal?
Equal to 0.
Set this equal to 0 and that equal to 0? Or what do you mean?
Like put it in a matrix and then make it equal to 0.
Okay, and how would you do that? What would it look like?
1, 0, negative 1, 2, 1, 0, 1, 1, 1.
And then you set that equal to 0?
Yeah.
Well, technically, the way you're saying it, you augment it with 0, but the reason why is, again, you go by the definition. If you set C1 times this guy, plus C2 times this guy, plus C3 times this guy, set that equal to the 0 vector, but in R3 with the standard operations, this is just 0, 0, 0. And so, yes, ultimately, you can multiply out, you'll get a system of equations with C1, C2, C3 as the variables you want to solve for. The first column is the coefficients of C1, so that'll be 1, 2, 1, 0, 1, 1, minus 1, 0, 1, 0, 0, 0. And now you want to find the solutions to this system. So you can do the reducer echelon form, which I believe I did just to save time. And this guy became 1, 0, minus 1, 0, 0, 1, 2, 0, 0, 0, 0, 0. Conclusion. Huh?
It's linearly dependent.
Dependent. Why?
There's infinite solutions.
Infinite solutions. Right, remember, to be linearly independent, only one solution must exist, which is the trivial solution. The fact here that there's a pivot in the C1 column, there's a pivot in the C2 column, there's no pivot in the C3 column, so basically your C3 can be literally anything. And for each value t, you can get a bunch of values for the other ones. So there'll be multiple solutions, an infinite amount in fact. So it turns out that these guys are not linearly independent. Which means one of them is redundant. Right? There's one of these guys that I can solve for in terms of the other guys, and which you can get to that by doing the solution for the system. But I just wanted to stop at whether it's dependent or not. So if you look at B, also, by the way, you can also, another check would be, since this happens to be square, we could have used the determinant. The determinant of 1, 0, minus 1, 0, 1, 2, 0, 0, 0. You'll realize it's equal to 0, which means, you know, according to Kramer's rule, there's no unique solution. So, no unique solution. One way you can see that is to apply Kramer's rule. In B, you do a similar thing, C1 times the first vector plus C2 times the second vector plus C3 times the third vector. Set that equal to the 0 vector in R3, which happens to be the vector of all zeros. This means you would get the system where that's your C1 column, C2 column, C3 column. We can do the reducer echelon form of this guy. And I believe it was, yeah, this one actually reduced to the identity. So now conclusion. They're linearly independent. Because clearly here C1 has to be 0, C2 has to be 0, C3 has to be 0. Also, you can notice that the determinant of 1, 2, 0, minus 1, 1, 0, minus 2, 1, 1 is non-zero. So you could do that check if you want. If it's square, you can always do that check. Okay, so that's how you check. If you're ever asked to determine whether or not a set of vectors are linearly independent, just set up this equation that's in the definition. Pick the right 0 vector for the set that you're looking in with the standard operations and see if there is a non-trivial solution. And that's the only, and if there's a non-trivial solution, it's dependent. Only the trivial solution exists, it's independent. Let's talk about some theorems here, which is going to help us out later. So I'll write them down. I might just talk about them, but we're not going to cover them. Theorem. A finite set that contains the 0 vector is dependent or independent? What do you think? set with one vector. This is called a singleton. Is linearly independent if and only if C S equals B1, comma B2. So with 2 vectors specifically, is linearly independent if and only if V1 and V2 are not multiples of each other, or scalar multiples of each other. Well, finite set that contains 0. What do you think? Right, so I have like B1, B2, blah, 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 Bn, and then there's the 0 vector just hanging out. Dependent or independent?
It's part of that set of vectors, right?
Yeah, the 0 vector is actually in the set of vectors. Is that set dependent or independent? Huh? Dependent? Why would you say that?
Because you could have any constant multiplied by the 0 vector.
Right. So if I were to set that up in the equation, C1 V1 plus da da da, Cn Vn plus Cn plus 1 0 equals 0, I can just make all of these guys 0 and then put 1 here. And I would still get 0. That's a non-trivial solution. I can literally pick anything I want to multiply the 0 vector, and even if everyone else gives me the trivial solution, that guy can mess up and then the whole thing goes to hell. So once the 0 vector is contained in your set, it is automatically dependent. Linearly dependent. And the reason, again, once you paying attention to the definitions are important because anytime you want to answer a question about some object, it's really you just matching it up with the definition. Does the definition work or does it not work? A set with one vector, it's linearly independent if and only if what? All right, so there's literally just one guy to worry about. C1 V1 equals the 0 vector.
It's a 0 vector.
Huh?
It's a 0 vector.
It's not the 0
It's not
vector,
the 0.
right? Because if this guy is the 0 vector, then any C1 will work, not the trivial solution. So he has to not be 0 for this to be dependent. So if the vector is not the 0 vector. By the way, part B of this leads to a kind of convention. We'll see later. Part B leads to the fact, which is really a convention, something that the spanning set and basis, which we'll talk about soon, of the 0 vector space Right, so there's a vector space that contains only the vector 0. So if we want to talk about a list of vectors here that are linearly independent that span the set, i.e. a basis for the set, it turns out that it has to be the empty set. It can't be this vector containing 0 because it would be dependent in that case, and that kind of messes everything up. Mostly we take this by convention, especially at this level. To actually be able to prove something like that, it will take some serious set theory, which is way beyond the scope of this class. There are a lot of other things that we'll take for granted here, like the fact that every vector space has a basis. We'll talk about basis later, but it's not really something you can prove with what we've seen in this class so far. You kind of need to go beyond linear algebra. There's one thing more ubiquitous than linear algebra. Like we said, it's kind of in everything. In fact, again, the way your solutions behave in a differential equation, for those of you taking differential equations, because of this fact right here. That's why when you're solving the differential equation y prime equals y, they say there's only one solution, right? Which the solution was c e to the t. And you're like, that's an infinite number of solutions. No, it's only one, because every time you multiply a constant, it's really no different. It's redundant, right? So there's only one solution to a first order differential equation. And that's the language comes from this fact here. But yeah, I'll talk a little bit more. I'm hoping to get to bases today. I think I will. Skipping the quiz in hopes that I'll get to bases, so we better get to bases. Another theorem that's going to be important. Let S be a set of vectors in V. And uppercase V is always going to be a standard notation for a vector space. Actually, this one I want to apply specifically to Rn. Then, if R is greater than N, then S is linearly should this be independent or dependent? I think it's dependent. Right, so like if I'm in R3 and I take a set of 4 vectors, will that set necessarily be dependent set? Let's make it easier. Let's say I did R2. Like, how would you justify it? For example, in R2, say we take 3 vectors. Right? So this is like the number of vectors is greater than the dimension of the Euclidean space that we're in. So let's say I have V1 equals, it's R2, so I can just write it like this. V2 equals CD, V3 equals EF. Will those vectors be dependent or independent? Yeah? Independent? How would we check? Plug it into the thing. So if you take C1, V1 plus C2, V2 plus C3, V3 equals the 0 vector in R2, which is just the vector 0, 0, ultimately that becomes the following. That becomes A, B, C, D, E, F augmented with 0. Now what can you tell me about that system?
That's more variables.
There are more variables than there are rows, which means at most, right, best case scenario, we have 2 pivots here. Right? It's only possible to get 2 pivots based on how we set up pivots, which means we will have at least one parameter, which kills the unique solution. Right? And of course, if there are more columns, it's even worse. We'll have multiple parameters. So it turns out, if you know you're in a set where, we'll talk about this later, the dimension is n, if you have more vectors than the dimension of that set, it turns out you'll always have a dependent set. So that's actually dependent. This fact will come down to bear when we're talking about dimensions. There are going to be some facts about dimensions where knowing these things, it's going to come in useful.
Further theory.
I should mention as well, BTW. We actually discussed this last time, but I just want to remind you so you can have both of them together. If R is less than n, then you can say S does not span R. So if I'm in 3 dimensions and you only give me 2 vectors, there's no way I can use those 2 vectors to construct any other vector in the space, right? Give me 2 vectors, at most I can create is a 2-dimensional space, so if I live in 3 dimensions, I'll never get the entire space. We'll talk about that a bit later. And so the idea is here, we're going to want to be able to talk about a set of vectors that are both linearly independent and span the set. Obviously the sweet spot is going to be when the number of vectors is equal to the dimension of the set. That was going to be the perfect number of vectors to do what we need to do. Yeah?
So R can only be equal or greater than n for it to span.
For it to span, it has to be greater than or equal to n. For them to be linearly independent, it has to be less than or equal to n. Which means if you kind of want both to work at the same time, you kind of need equality. And we're gonna talk about that in the dimension section. That's 4.5. We'll talk about that. But at this point, we have these facts that we're picking up along the way. What else did I want? We do want to talk about functions as well. Let's look at C continuous functions. Are the following functions linearly independent? So let's say I gave you 3 functions to consider. One function of x is cosine of 2x. The other function of x is sine squared of x. Third function of x is 1. Linearly independent or dependent? What do you think? How would you check? Let's actually do both. Let's actually do 2 examples here. Let's say, again, I choose 2 functions. E to the kx, where k is a scalar. The second function is e to the lx. Let's assume here k is not equal to l. And I want you to describe to me, are these functions independent or dependent? Right, questions like this are very important in differential equations for one place. Turns out a fundamental set of solutions is a set of solutions that solve a differential equation that are linearly independent. And it must span the solution space, so you have to have at least n of them. And they're linearly independent, so you have to have exactly n of them. What do you think? So first one, part A. Yeah? How do you know?
I mean, you can just set like, C cosine 2x plus B sine squared x. Yeah, C2 and C3 equals 0.
So the zero vector here is the zero function.
Yeah, so I mean, the trig identity for sine squared x, 1/2 minus 1/2 cosine 2x.
Yeah, so you remember there's a trig identity. So recall, for 1, we know that cosine of 2x is equal to 1 minus 2 sine squared x. Which means that cosine of 2x plus 2 sine squared x minus 1 is equal to 0. In other words, C1 equals 1, C2 equals 2, and C3 equals minus 1 is a solution. So they're dependent. That's a non-trivial solution. F1, F2, F3 are dependent. So for example, in the differential equations context, again, for those of you who've done it, if you're trying to solve a third order differential equation, and these were the list of functions that you assume are the solution, it means you don't actually have 3 solutions. You have at most 2, and you need to keep looking. Because there's another solution out there. Let's see. Did someone raise their hand? Okay, let's talk about B. E to the kx and e to the lx, where k is not equal to f. So for example, e to the 2x and e to the 3x. Dependent or independent? So I can take c1 e to the kx plus c2 e to the lx equals the 0 vector for the functions, which is just a 0 function. What can I say about that? Yeah?
You factor out either e to the kx or e to the lx, whatever you want.
Okay. So let's say I factor out e to the kx.
And that, you get rid of that e to the kx term. Or
Okay, so what would that become? This would be L minus K.
Right.
What does that tell you?
You need the second term to be 0. It's like e to the kx.
Right, so this means e to the kx equals 0, or c1 plus c2 e to the L minus k x equals 0. Obviously, that's never true. Your exponential is always greater than 0. So this would mean that c1 plus c2 e to the L minus k x must be equal to 0, which means
C1 equals C2 equals 0.
The addition of 2 positive.
well, I
C1
don't
could be
know that
negative.
this
Yeah,
is
never mind.
positive. I mean, there are ways to actually consider a solution to this, but at this point you're like, okay, I'm not sure so far. So I'm going to give you a way that we can actually look at it. So it turns out there is a systematic way to solve this provided one condition. There is a way around this, provided the n, let's suppose I'm considering n functions, the n functions being considered are at least n minus 1 times differentiable. So let's see how we can use that fact to help us. And remember, not all functions are differentiable a certain number of times. There are some functions that you differentiate them once or twice, you eventually end up with something you can't differentiate anymore. But assuming that we can differentiate it at least n minus 1 times, there is a workaround here. So I'm going to show you the workaround, and then we're going to, again, tackle this same problem. So the thing given, let's say I had C1, F1, C2, F2, plus Cn, Fn equals 0, and the Fi are n minus 1 times differentiable. What that means is I can just start taking derivatives. Now if I were to take the derivative of this, what would I get? C1 F1 prime plus C2 F2 prime plus Cn Fn prime equals 0, 0, 0. So I do that again. And I'll continue that, and I do that n minus 1 times. So I end up with C1 to the n minus 1th derivative plus C2 F2 to the n minus 1st derivative plus Cn Fn to the n minus 1st derivative. What did I just create? I created a system of equations. Now, what is the solution that I care about? It's actually the solution for the c's, right? So I'm kind of going to flip the switch here, and I'm going to think of the c's as the variables that I need to solve for. And so the functions I would think of as the constants. And so what I have, this is an n by n system. In the variables C1 to Cn. So if I think of those guys as my variables, how can I tackle this system? I know there's at least one solution because it's a homogeneous system, all of them equal 0, but how do I know whether or not there are more than one solutions? Ideas? Yeah?
If they all differentiate down to 0, then you have a problem. If every single one of your functions will become 0 at some point, then you have a problem. Because then you'd have a row of zeros.
Sure, this is true. But how am I going to tell that ahead of time? How would I know if I get a row of zeros eventually? Or maybe through some other mechanism get a row of zeros? Maybe I can write this a little bit more suggestive. I can write this as a matrix equation. What would be in here? The c's. Because I'm thinking of those guys as my variables. So what will be left over here? Well, F1, F2, Fn, F1 prime, F2 prime, Fn prime, all the way down to Fn minus 1, n minus 1, n minus 1. Okay, tell me about that system. What can we say about the system? the determinant of what? This guy, let's say I call this A, just so I don't have to copy that. Huh?
Zero.
Non-zero. By Kramer's rule. So I have a bunch of functions that are n minus 1 times differentiable at least. I know that if I find the determinant of a matrix that looks like this, and the determinant is non-zero, they are linearly independent, because it guarantees a unique solution. And I know 0, 0, 0, 0 is a solution, because it's homogeneous. And this works. And of course, because these are functions, you have to worry about things like intervals where they're defined on intervals. So this kind of leads to something else. So here's a definition. The determinant f1 fn f1 to the n minus 1 derivative down to fn to the n minus 1 derivative is called my differential equations, people. It's called a Wronskian. So there was an entire chapter in differential equations devoted to this guy. It's named after a mathematician whose last name is Wronskian. It's called the Wronskian of the functions f1, f2, f3. And we denoted by, you can say w of the functions f1 to fn, or just w if understood what functions are being considered. And it's called a Wronskian of the functions. So if you ever have a bunch of functions, a solution to a linear differential equation, and you want to know, are these linearly independent? You just throw them into this. A priori, they're all differentiable because they're solutions to a differential equation. And so you throw them in this matrix, and as long as you find the determinant of that, as long as it's non-zero, we know it's a unique solution. And that brings us to the theorem. If the Wronskian of f1 to fn not equals 0, identically on an interval I, then f1 to fn are linearly independent on this interval. One thing you should note, converse is not true. i.e., if the w is equal to 0, then no conclusion can be made without additional So the counterexample to this was developed by Peano, the same guy who came up with the Peano axioms to define the integers, the natural numbers. I believe the functions he used was y is equal to x squared and y is equal to x times the absolute value of x. Turns out that the Wronskians of those two functions will always be 0, but they're actually independent on any interval that contains 0. So it's not that, you can't say if the Wronskian is 0, they're definitely dependent, it could be independent. So let's see here. Oh, let's go back to that example then. F1 equals e to the kx, F2 equals e to the lx. And so here I can find the Wronskian of these guys. That's e to the kx, e to the lx. Differentiate one time, that's k e to the kx, l e to the lx. Then take the determinant of this. So this is L e to the k plus L times x minus k e to the k plus L times x. This is equal to L minus k times e to the k plus L times x. And since L is not equal to k, this is not 0. Because the only way for this to be 0 is if this is 0 or that is 0. This is never 0, it's an exponential. That's never 0 because L is not equal to k. So this means they are linearly independent. Another reason in differential equations, when you got two exponentials as a solution of a differential equation, as long as the powers were different, you realize that, oh, these are linearly independent. And you just move on with your life. You never actually check it because you know this is the sort of thing that's going to work out. Again, if the Wronskian is 0, you can't really be sure, but in this case it's easy to check. Notice that if k equals L, then you can see that 1 e to the kx plus minus 1 e to the lx would actually be 0, so they would be dependent in that case. So the Wronskian would be 0, but you can't really make a conclusion from that, but it's actually not hard to just solve the equation, and you would definitely get 0. You will get a non-trivial solution. So, i.e., you can look at exponential functions, and as long as the powers are different, they're actually linearly independent. E to the kx and e to the lx are linearly independent if and only if k is not equal to L. Right, so there are multiple contexts. The moral of the story is there are multiple contexts in which we're going to want to talk about independence. It doesn't have to be vectors in the general sense. It doesn't have to be matrices. It could be functions. It could be polynomials or exponentials or anything. There are multiple contexts in which we might want to talk about things being independent from not being independent. I have one more example here, but I think that's kind of enough. Let's move on to 4 point. I kind of defined this already, what a coordinate is, but let's look over it and see why it's a unique identifier. Coordinates and bases. Bases, by the way, is the plural of basis. If you're talking about a specific one, it's called a basis. The plural is basis. Or a definition. Let V be a vector space. And S equals V1 to Vn. Be a set of vectors then we say S is a basis for V if two things hold. One, S spans V, i.e., every vector in V is a linear combination of vectors in S. Right, that's what it means to span. We spoke about that a couple lectures ago. And two, S is linearly independent. i.e., no redundant vectors more specifically C1 V1 plus da 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 Cn Vn equals 0 only has the trivial solution. So if I take a set that spans a vector space and the set is minimal, there are no redundancies in the set, then that set, I call it a basis for the vector space. The vector space can literally be constructed using this set of vectors, and you can get every vector in the set. You can get the entire vector space by taking linear combinations of these vectors.
Also,
Yes?
can you come over redundant vectors? What is that?
Huh?
Redundant vectors, what is that?
Redundant means you don't need all of them. Like if one is just a linear combination of the others, you can throw it away. You don't need it. Right, so redundant means it's not needed, it's extra, right? So if you can span the space and there's nothing extra, you're called a basis for the space. Yeah?
That means the dimensions of V has to be the number of vectors.
That's where we're heading, yes. In 4.5, we're going to figure that out. So, yeah, based on the two facts that I mentioned here, that says if your R is greater than n, then it's definitely dependent. If your R is less than n, then it doesn't span. They have to be equal to be both independent and span. So this kind of means that any basis for a vector space, if it has n vectors, then the dimensions of the vector space must also be n. And in fact, this is going to be the definition that we're going to take for dimensions. We call something n-dimensional if there are n vectors that form a basis for the set. Right? So R2, why we can call that a two-dimensional space is because we can actually find a set of two vectors that form a basis for that space. Example, the set B equals I comma j is a basis for R2. Right? We proved it separately that these guys are linearly independent. We also proved that they span the set. Any vector in R2 can be written as a linear combination of I and j. These two things together means that forms a basis for the set R2. Right, and of course, examples again, E1 da 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 to En is a basis for Rn. Tons of examples here. 1 x da 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 xn is a basis for Pn, etc. Right? In fact, these guys are sort of the brain dead way you build these sets up, so that's why these are called the standard bases. They're the ones that you can find a basis for the set without having to think too hard or work too hard. Because once you just set up this linear equation, you get the answers by just equating the coefficients. So that's why they're called the standard bases. These are the standard bases. And they go with, of course, the standard operations. right? So ij is the standard basis for R2. Fact here. It is not a coincidence that I'm saying a basis, because bases are not unique in general. In fact, based on the last two lectures, we kind of showed this with a set of vectors. There was the example here. When we looked at those three vectors in R3, 1, minus 1, minus 2, 2, 1, 1, 0, 0, 1 is a basis for R3. We showed they actually spanned R3, we proved that in the last lecture, and we just showed in this lecture that they're linearly independent. We actually did that for this set, meaning this is another basis for R3. We're used to thinking of the basis for R3 as ijk, but that's out of convenience, really. I could take many bases. R3, for example, has an infinite number of bases that you can choose from. Not all sets are like this. For example, the zero vector space, there's only one basis for the zero vector space, namely the empty set. But there are cases where you have multiple bases for any set. Even an infinite amount. Rn, for example, has an infinite amount of bases. Sure, there's the standard one that we all like using for convenience, but there are many others. So bases are not unique. Another fact. However, with respect to a particular basis, the linear combination that makes up any vector is unique. Let's say the basis here is v1 to vn. Then x in v is uniquely expressed as, let's say, c1 v1 plus da 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 up to cn vn. There's literally only one way to write as a set of as a linear combination of these vectors. There's no other way, right? These coefficients have to be the same. And you can actually do this by a proof by a contradiction. Suppose there is another way. Say I could write x as a1 b1 plus da 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 plus an bn, and it's not the same as writing c1 b1 da 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 as cn bn. Then what I can do is if I think of this as equation 1, that is equation 2, I can subtract them. This means x minus x gives me the 0 vector, and then I would have here a1 minus c1 b1 plus da da da, an minus cn bn, by taking equation 2 minus 1. But what do I know about the v's that can show me that these are actually the same? They're independent. Which means setting up a linear combination equal to 0 means that the coefficients have to be 0. This would mean that your A1 minus C1 must be equal to 0, which is equal to, literally all the AI's minus CI's must be equal to 0. And so you get that AI equals CI for all I. And so this combination, and therefore it's a contradiction because I just proved that they're actually the same. So if I pretend there's some other way to write down this vector, it turns out that it's exactly the same way as I did before. There's literally only one way to write down, with respect to a basis, there's only one way to write down any vector. Which tells you that the coordinate of a vector is unique with respect to a basis. This is referred to as the uniqueness of basis representation. It shows the coordinates. I defined this in the last class. Of x is unique with respect to a particular basis. There's only one set of coordinates that will give me the vector x. There are a couple things that we can take away right away from this fact. One is a little more difficult to derive from, but one is straightforward, is C1 is a unique location of x. We can think of this as a locating factor in Rn. So if my C1s are real numbers, then this coordinate is related to a vector x in a unique way, and so it's like the address of this vector. Can anyone tell me a bigger consequence? I know we're kind of in a rush here, but we'll end right after this. This means, let's say here I have a vector v and a vector Rn. This basically tells me that a random x here with respect to a basis, it's uniquely identifiable with some vector over here. Let's call it vector c. Can anyone sort of tell me a consequence of this? Something that's really nice. If V is finite. The infinite case is a little bit more weird. But as long as I have a finite dimensional vector space, it doesn't matter what the vectors look like. They can be words, phrases, functions, matrices, anything else. There is a unique way to connect elements of that set to the set Rn. In other words, the guys in here will behave exactly like the guys in Rn. Moving guys around here is the same as moving guys around in there. Right? There's a unique way to actually do this. And you can do that for every single vector because the definition of a basis says that we can attain any single vector. Now this we're kind of jumping ahead into the topic of isomorphisms, but it's a very important idea, and this is kind of where it's coming from. This is kind of how we know it's going to work. So if one vector space is kind of inconvenient to work with, all I do is figure out a way to connect it to vectors in Rn, do what I need to do in Rn, and translate the answer back. right? I can actually study vector spaces by studying a corresponding Euclidean vector space, which we've spent all of calculus studying. So we know a lot about Rn. Right? So for some other random vector space, it's a very useful fact that we can actually make this connection. And we can do it in a unique way. There's going to be no ambiguities. This vector represents that vector, and there's no questions about it. There's no other vector that could represent it. It has to be that guy. We'll stop there, and we'll see you on Thursday. We'll talk about a little bit more about this and then talk about dimensions.